Hi and welcome to the lesson of real analysis. And in this class, we are going to start the discussion on sets, open sets, closed sets, neighborhood of points, interior points, limit points, and other important topics. So let's start with the neighborhood of a point. So a set N, let's say we have a set, we call it N. For instance, we have a set A, let's say A comma B. It's a set. We represent it like an open interval, but it can be any set. For instance, it can be 1 over n, or such that n belongs to n. It can be a finite set or infinite set. So a set n is called a neighborhood of a point P. So this set that we have taken, or any set, will be a neighborhood of a point P of any point contained in N, that is point P. For instance, if I draw this interval AB here, so there is some point P inside this interval. If there exists an open interval I containing P, so we again require an open interval that contains this point P. So if we have an interval like AB, and there's a point sitting between these 2 points, then we have to have an open interval I that will contain this P, right? So if there exists an open interval I containing P and contained in the set, so that is P belongs to I, so we should have an open interval I. Let's say this interval from here to here, this is I, and this whole interval from A to B is N. So the interval is N is from A to B, and the interval I is from, let's say this is C and this is D, C to D. And we can see that this interval CD is contained in AB, and then this P is contained in this interval I. So P is contained in I and I is contained in N. So if this condition is satisfied, then we call that the set N, this whole set N, that is AB, is the neighborhood of point P. So, and let's look at one more definition. It follows that an open interval is a neighborhood of each of its points. All right, so for any open interval, for instance, if we take 0, 1, we can see that if we draw it on a real line and we have 0 here and 1 here, and if we talk about any point inside this set, inside this interval, let's say if we want to take a point here and call it P, then if we take the neighborhood of this P, so these the all points around this P from left and from right as well, these all points are the neighborhood of P. So all points in this open interval are the neighborhoods of P. So it means that this statement represent similarly this same thing. So it follows that an open interval is a neighborhood of each of its points. Okay, and then again, one more way to define this neighborhood is that let X be a point that belongs to the set R, and a set N equals, this is representation for set that N X comma epsilons is called neighborhood of X if there exists epsilon greater than 0 such that X minus epsilon comma X plus epsilon is contained in N. So again, this is the same thing that if we have a point in any set, for instance, we have a point X and we need to move forward. So it's X plus epsilon, and here we have X minus epsilon. So if we make an interval like this, so this interval should be contained in the set. It should be contained in the set. So we can go as far as we want to go from this point to left and this point to right, but we have a restriction here at the boundaries, so we cannot not cross the boundaries. So then despite of moving from to right and left, we can see that we are contained in this set, that is the, we call it n, this whole set. And then we can move from x to right, from x to left, x minus epsilon, and from x to right, x plus epsilon, and we will be contained in this set n. So this is actually the definition of the neighborhood. So every point here, every point here in this set is neighborhood of this point x. And in case of the closed interval, we can see that not every point is neighborhood, because if we have a closed interval, which means that we can just draw here that if we have a closed interval, for instance, it's closed from the left and it's open from the right, then if I want to find the neighborhood on this point, because now this point is included in the set. For instance, if we call it 0 comma 1, so 0 is included in the set, and if I want to find this, let's say call it point x, and I want to find x plus epsilon and x minus epsilon, then what will happen eventually? I will be out of the set when I want to find x minus epsilon, because this thing here is not contained in this set, right? So in the case of the intervals other than open interval, not every point is neighborhood of x. So only in open intervals we will have all the points will be the neighborhood of every point. Okay, then we want to talk about the interior point of a set. So the definition of the interior point says that a point x belongs to the set E is an interior point of E if there exists epsilon greater than 0, such that this symbol is for such that x minus epsilon comma x plus epsilon is contained in E. So this is very obvious from the definition that we need such points, that is x, and if we have x plus epsilon here, x minus epsilon here, so we need such points that are actually contained in the set. So if we move from x to right, if we move from x to left, these all points that are contained in the set, if they are contained in the set, then they are called the interior points. Okay, so we'll take an example to clarify what we mean by interior point. So it is necessary that for any point in the interval, we should have to have a neighborhood on the right side and left side. By neighborhood, we means that on both sides, right? So we should have some points. Let's see this example. For instance, this is a semi-open, semi-closed interval. For here we can draw it on a real line. So this is -2. This is closed. So let me draw this closed interval with dot with a thick dot. So this is closed, right? And there this is open 4. And then we have a singleton 6. So we can just make it like in a dotted line like this, and somewhere here I have a singleton 6. So here it's a singleton 6. So this point, let's call it 6. Now if we want to find the neighborhood of every point, so let's talk about this point first. Now this point is included, so we can stand on this point, and we can stand on this point, and if we expand, if we want to expand in both directions from left to left and right as well, then we can see that actually onto the left, if we expand, we are moving out of the set. We are moving out of the set, which means that if this point is x, or let's say this point is -2, but we have -2 plus epsilon, but we don't have -2 minus epsilon, because on the left side, whatever the points are, they are not included in the set. The points on the right are in fact in the set, but points on the left are not in the set. So -2 cannot be the interior point of the set. But if we move inside -2, if we omit -2 and we move inside -2, and we can take any number closer to -2, as much as close you can take closer to -2. Then if we want to expand from that point, and we can expand, and we can uh, remain inside the set. So every point inside -2 is indeed an interior point. And now what about this 4? So this 4 is not included in the set, so we cannot stand on 4. So we can stand just inside 4. So if we stand here just inside 4 and we want to expand, so we can expand in the set, and this x plus epsilon and x minus epsilon exist for this point 4, because this point is not included. We cannot stand on the point, so we need to be inside the point. And if we need to be inside the point and we want to expand, so we can expand in being in the set. So this point 4 is indeed an interior point. So this point, no, sorry, not 4 is interior point, but 4 is excluded, and we can make a set of interior points. Right now we will make a set of interior points. I will show that how to write these interior points. So 4 is in fact not included in the set, so it's not an interior point. But all the elements just before 4 are the interior points. And this singleton 6, again, if we stand on the singleton 6 and we want to expand, then again we are going outside, because 6 is singleton element and no other elements are in the neighborhood of 6. So again, this not work for 6. So now we can say something about the interior point of this set. And so the interior points of this set are simply -2 to 4 open, right? Because we can be being inside this set, this open interval, we can find the room for breath. So we can easily stand inside this interval. And this 6 is not the interior point, because we cannot stand on 6 and find the neighborhood. If we stand on 6, we cannot find any neighborhood beside the element 6. So this is not the interior point of the set. Okay, now for this interval again, we have -1. Okay, we have union of intervals and a singleton element. So again, this is open -1, then this 5 is closed, then there is a singleton element. Okay, we can make dotted lines for singleton element like this. Okay, it's 7 somewhere here, and then we have a straight line again from 10, let's say. Okay, so it's 10 and going to infinity, and this 7 stands somewhere here. For instance, we mark it with green. Okay, now again, if we start from -1, so we know that this -1 is not included in the set, so we cannot stand on -1, so we need to be inside -1. So if we are inside -1 and we want to expand, so it's okay that we are going to find a positive epsilon and negative epsilon for x. So being inside -1, so -1 with open, it's an interior point. And again, all these points are the interior points up till here. And on 5, again, the same thing. If we stand on 5, because 5 is included, and we want to expand our hands, then again the failure is there. So on the right of 5, we don't have any neighborhood, so we cannot include this 5 to the set. But just before 5, as close as you think to 5, you can think about the points, and we get interior point excluding 5. So all the points excluding 5 in this set will be the interior points from -1 to 5. And then again for 7, we don't have any neighborhood in the right and in the left as well, so it's not an interior point. But union this 10, now we can stand inside 10 and we can expand the hands and we will get positive and negative epsilon. So this 10 is fine, and to infinity, these all points will be the interior points. So this is the philosophy of the interior points. We can write in this manner the interior points of the sets. Now we talk about open set. So an open set. So what is an open set? Okay. So set A is open if for each x belongs to A, means for every point belongs to A, there exists an epsilon greater than 0 such that x minus epsilon comma x plus epsilon is contained in A. So this definition is very much compatible with the definition of interior points. We can see that because in the definition of interior points, we also mentioned this thing that a point x belongs to E is an interior point of E if there exists epsilon greater than 0 such that x minus E epsilon comma x plus epsilon is contained in E. So this definition is very much compatible with that definition, and it's the similar meaning that if we have a set A, if we have a set A, for instance, so and we can take any point in this set A, we can take any point in this set A, for instance here, for instance here, for instance anywhere we can take, being inside the set, because now this is an interval. For instance, we are talking about interval, let's say this is 1, this is 3, and 1 and 3 are excluded, so we need to be inside this 1 and 3, and we can stand anywhere and we can take any point P, so we will find some neighborhood on the right, some neighborhood around point P. So we will have the points in the neighborhood to right and in the neighborhood to left as well. So that is the definition of the open set, and equivalently we can say that set A is open if all of its points are interior points, that is interior of A equals A. So for instance, let's talk about this example. So to understand the meaning of this statement, let us consider this example, that is 1, 3. So what does it tell, 1, 3? So similarly, if we want to find the interior points of this 1, 3, what we are going to do, we have an open interval, so 1 and 3 not included in the set, and we can stand here around 1 and 3. So we can stand anywhere between these, and we want to expand, we can expand, and easily we will find the neighborhood inside the set. So now this we can see that the interior of this set is again 1, 3. So this is the meaning that the interior is equals to the set. If the interior is equals to the set, then we call it an open set. So an open set, we have the definition that set A is open if for each x, like for each element of the set, any element of the set, there exists some epsilon greater than 0. Epsilon greater than 0 simply means there should be like points. There should be points. For instance, if I am standing here and I call this point x, and this point x belongs to the set 1, 3, which I am talking about, this set A, right? So this is set A in this context, and then any point on x, like here, x belongs to any point. Or I say if I'm taking 2, for instance, here, so I will call it 2 belongs to this interval. So in this context, now this x, element x that I took here is 2, right? So this 2 belongs to the interval 1, 3, and there exists epsilon greater than 0 such that, for instance, if I such that x minus epsilon, okay, so I want to move from 2 to the left side, and I want to move from 2 to the right side. And I can see that I have these all points contained in this set. Okay, these all points. From here I can move left as much as I can, but there's a restriction here at 1. I cannot cross this 1, or neither I can stand on 1, so 1 is excluded, 3 is excluded. So these all points are contained in the set A, right? So this is the meaning of this statement, that x minus epsilon and x plus epsilon are contained in A. Okay, and that is not necessary that the distance is, for instance, if we can see here that this is x minus epsilon and this is x plus epsilon, and this is statement just it looks like that the statement is saying that the distances should be similar. For instance, if this is x here, for instance, this is the interval 1 3. If we are moving forward, we have some distance x plus epsilon, and if we are moving backward, we have some distance epsilon. So if we, for instance, if we are standing here, if we are standing very close to 1 and 1 and 3, okay, so if this is x and we want to get some distance forward, for instance, we want to move some distance forward, and we call it x plus epsilon. Now we are adding something because we are moving forward, so we need to add something in the x where we are standing, something in the position we are going to add. And similarly, if we want to go back, we will get some uh, x minus epsilon distance as well. So this is the simple meaning. But yes, all these points of around x are neighborhood of x, and that is also the definition of the neighborhood. So the neighborhood of x is contained in the set, right? So this is called the open set. Okay, we have some examples of open sets. A non-empty open finite set is not open. Okay, if we have a finite set and it's non-empty, for instance, 1 2 3, this is not an open set. Okay, because this is finite. So every finite non-empty open set is not open. Okay, so finite set is not open. Q, the set of rational numbers, not open. Set of integers, not open. Set of natural numbers, not open. Set of these irrational numbers, not open. Okay, so why set of rational numbers is not open? Because it not fulfills the definition, because in the set of rational numbers we have a lot of irrational numbers in the neighborhood of Q, because we studied in the previous lessons some properties of rationals that we call it the incomplete. So talking about the completeness of real numbers, we also talk about the non-completeness of rational numbers. They are not complete because they have a lot of points of irrational numbers, a lot of irrational numbers in their neighborhoods. So this is not open because the neighborhood is not contained in the set Q. Okay, so if you take its neighborhood, the neighborhood of rational numbers, so in their neighborhood there are irrational numbers which are not the part of rational numbers. So the neighborhood is not contained in the set, in the universal set that is Q. Okay, so same for the integers, same for the natural numbers, same for the uh, irrational numbers. Again, now we have the definition for limit point. A point x belongs to R is a limit point of set E. Okay, we have some set E, and we will call a point x belongs to R. X belongs to R. We are taking the set as real numbers, set of real numbers, a limit point of set E if for all epsilon greater than 0, the set x minus E, comma x plus E intersection, x minus epsilon, comma x plus epsilon intersection E contains infinite many points. Okay, so let's try to understand the statement by some figure here. Let's say we draw a line here. Okay, now consider that there are a lot of important points in this definition that we need to consider. Now, for instance, they have said that X belongs to R. They did not call that X belongs to the set E. Okay. Now, this makes the sense that limit point may or may not be in the set that we are talking about. For instance, I will give examples. Okay, a point X belongs to R is a limit point, is said to be a limit point of set E, of some set E, if for each epsilon greater than 0, the set X minus epsilon, X, this X, right? X minus epsilon comma X plus epsilon intersection with the set contains infinite many points. Okay, all right. This means that if we have a point, if we have a set E, for instance, this is a set E. This is my set E, for instance. This is point, let's call it A. This is point B. Okay. Then any point in this set, according to this definition is saying that any point in this set, any point in this set will be a limit point which possess following quality. What quality? That for each epsilon greater than 0, the set, then the set what I'm making, for instance, if I am talking about X, this point, okay, this point, let's say this is my X, this is my limit point, then what does it mean? It means that the neighborhood of this X, the neighborhood of this X with the intersection of this E set E, will be infinite. Okay, this thing will be more clear with the examples. When we will move on to the examples, these things will be more clear. Okay, so, and this point may or may not be in the set. For instance, this point can be here on A, whereas this A, which I make an as open interval, is open. So this A is not included in the set E, but this can be a limit point because this can accumulate infinite points beside it, right? And when we take intersection of this small interval with this set E, then it will be infinite. Okay, let's talk about example. For instance, we have a set 1 over n. Okay, we want to draw this set on the real line. So the elements of this set look like 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, and so on. Let's draw it on the real line. So my 1 is in the set here. Then I'm moving back. It's decreasing, 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 decreasing. Okay. And there will be a time when moving to infinity, there will be a time it will reach 0. But 0 will not be in the set, contained in the set, because we are not thinking about the infinity right now. We know that 1 over 0 is infinity, but we are not including this infinity in the set. We are only talking about natural numbers. But it is a sense that when we are moving in this way, by dividing by natural numbers and increasing in the order, then eventually we are going somewhere 0. But the 0 is not included in the set. This 1 is included in the set. 0 is not included in the set. Okay, now let us talk about the limit point of this set. Okay, now can we see any point in the neighborhood of 1, or any point here in this neighborhood? Is there any accumulation? This is the set E, for instance. Okay, set E is 1 over n, where n belongs to natural numbers, and we are going to find the limit point. And by the definition of the limit point, we need infinite, the intersection should be infinite. So x, whatever x we are choosing, whatever point, limit point we are choosing, the intersection with E should be infinite. This is the definition. The intersection should be infinite. Okay, so if we take this point, let's suppose 1 over 2, and if we want to look at the neighborhood, are there infinite points? There are not infinite points. In fact, there are in the neighborhood, there there are gaps, there are no points in the neighborhood. So after 1 over 3, 1 over 3, we have 1 over 2, we have 1 over 3 on the left side and 1 in the right side. So there are a lot of points missing between them. But as we move in the left direction and we move on, we can see that the distances are decreasing. For instance, initially this distance from 1 to half was 1 over half. Okay, from half to 1 over 3, it was like 1 over 6. So we can see that the distances are, and if we consider 1 over 1 lakh minus 1 over 99999, sorry, yeah, okay, so this distance will be very less, like 0.0000000 something. So the distances are decreasing and tending towards 0, which means that these points are going to accumulate on this 0. Okay, so when I will be standing at 0 and I will be looking at the neighborhood, for instance, neighborhood of 0, sorry, and if I add some points 0 plus epsilon, for instance, I'm taking till here epsilon, and 0 minus epsilon, this interval. Oh, and keep in mind one thing, that don't mix it with the neighborhood and with the open set. This is not the concept of the open set. This is just simple that this interval, intersection of this interval with E, will be infinite. It doesn't matter that this point x minus epsilon or x plus epsilon is in the set or not. But if one of them is in the set, for instance, in this case, x plus epsilon or 0 plus epsilon, that is right, everything to the right of 0 is included in the set, but to the left of 0 is not included in the set. For instance, this distance is epsilon, this is minus epsilon. So this is x minus epsilon, this is x plus epsilon, right? This is x plus epsilon. So now we can see that in this region, there are infinite points, and if I want to take intersection of this set that I'm making here, that is 0 plus epsilon and 0 minus epsilon, with the set E, I will have infinite many points, because there are infinite points that are accumulated in this region. So, and these all points belong to the set as well. Okay, so I don't need to bother about this region, because this is not included, but I don't need to be bothered because I need infinite points in the intersection. So I have infinite points in this region, 0 plus epsilon. In fact, this region is not included in the set, but I don't need to bother because I need an infinite intersection with E. So 0 plus epsilon is giving me an infinite intersection with E. So this 0 is the accumulation or limit point of this set. So this is the concept of the limit point. Okay, now let's look at this problem. We have 3 to the power 1 plus 1 over 3 comma 3 to the power 2 plus 1 over 3 squared comma 3 to the power 3 plus 1 over 3 to the power 3, and so on. Now if we talk about this example, we can draw it on the number line. It's good to draw it on the number line. So the least element will be 3 plus 1 over 3, which means that 10 over 3, for instance, somewhere here. Then we have 9, so it's 82 over 9. Then we have element 27 times 27 plus 1 over 27. So 27 times 27 plus 1 over 27. So it's bigger and bigger. It's getting bigger and bigger. We can see that it's getting bigger and bigger, and it will go to infinity. So there is no accumulation or limit point in this set, because nowhere uh, in the set, nowhere in the set or outside the set, uh, there is any limit point. And I forgot to tell you that in the previous example, this 0 was not included in the set. This 0 does not belongs to the set of E. So limit point can be outside the set, okay? And this is moving towards infinity. And on infinity, somewhere on infinity, but we cannot find out, we cannot figure out the number, that around what number the points are going to accumulate. So again, we are failed to find any limit point. So no limit point exists for this set. No limit point exists for this set. All right, now talk about this set. Again, on the real line, we can draw this set. So 1/2. Okay, 1/2. Let me make it on the line. Okay, so first of all, it will be 1/2, 2/3, 3/4, 4/5, so on. And then we have 1/2. Okay, 1/2 is the greatest element, then 2/3 is lesser than 1/2, then 3/4 is lesser, 4/5 is lesser, 5/6 is lesser. Just a minute. It's in this, not in this order. It's in increasing order. I'm sorry, because 2/3 is greater than 1/2, so we have 1/2, 2/3, 3/4, 4/5. So it's increasing. 5/6, increasing, increasing, increasing. And what happens if this thing tends to infinity? So we can see this is increasing, but each element is lesser than 1. Lesser than 1, 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 and each element is lesser than 1. But at some time, these all elements, the distances between these elements are going to be very, 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 very smaller, and they are going to be very, very near to 1. So the elements will look like near to 1. It will approach to 1. And in this manner, that 1/2, 2/3, 3/4, 4/5, and so on, so on, so on. And it will approach to the 1 here. If I take neighborhood at 1, left and right, so I will get 1 minus epsilon, comma 1 plus epsilon intersection with this set, what I call S, and I will get infinite points. All right, because we can see that as these numbers are increasing, as the order is increasing or the sequence is increasing, it's going near to 1. So for instance, if I take 1, this 99999 divided by 1 lakh, 1 lakh. So we are very, very near to 1. It will be 0.999999999 like this, something like this. So we are going nearer and nearer to 1, okay? So we have this 1 minus epsilon, comma 1 plus epsilon intersection as infinite. That's what we need. So the limit point of this set is 1. So the limit point, we call it LP, is equals to 1. Okay, now let's look for